Hello, this is David Cox, and this is my Physics 2212 Lab 3. The purpose of this lab was to calculate the magnetic dipole moment of a bar magnet and predict the magnetic field due to the bar magnet at an off-axis observation location. The physical concepts in this lab were basically described by the Biot-Savart law, or form of it, shown below, which relates magnetic field and magnetic dipole moment in this equation. The methodology used, I had a magnetometer app on my iPhone, which was used to gather the magnetic field data at various points along a meter stick. I used that data to calculate the magnetic dipole moment of that bar magnet, and then subsequently use that data to predict the off-axis magnetic field magnitude. The assumptions and approximations in this lab were as follows. The magnetic north was the only magnetic field accounted for, aside from the bar magnet, of course, leading to potential extraneous magnetic fields that were not in our calculations. Additionally, the position of the magnetometer in the iPhone was certainly approximated, although I got as close as I could. The results are shown below for the off-axis magnetic field as calculated, as measured. Additionally, the moment which was used to get these numbers was calculated as 5.7 Newton meters per Tesla, which will be shown in the next slide. This is just the math I used to stemming from that Biot-Savart equation I showed y'all to get the magnetic dipole moment from the observed values of distance and magnetic field. A GlowScript Python code was used to model an off-axis magnetic field due to that magnet. Note the value for the mu as defined on line 24 of the following code is the exact same experimentally determined mu as we showed in this slide. Here's some of my code. You can see here, these are just defining that nu that I spoke of. This is defining the basically Biot-Savart law. And then these are the results of that code. In GlowScript, you can see in orange the collinear components of magnetic field. Here in cyan, you can see the perpendicular components, and here you can see the resultant vector. And these results here, the magnitude of this was found to be 4.364 times 10 to the negative fifth Teslas, which was different, certainly, but still relatively close to the experimentally determined value of 2.17 times 10 to the negative fifth Teslas. And like I said, these values are off by about a factor of 2, but they're in the same order of magnitude, so a win is a win. Here are just some questions asking what if. First, what if the experiment had not properly compensated for Earth's magnetic field, as I did? Well, then the measured magnitude of magnetic field would be greater than it was. I actually, in the Excel spreadsheet, play around with that and found that it would be just only a few microteslas bigger, but still significant statistically. And then if two identical bar magnets with the same magnitude and size were used instead of one, the magnitude of the resultant would simply be larger. The direction of the field would not meaningfully change if you choose to roughly neglect the size of those bar magnets in relation to your observation location, which I believe was done in this lab. And that is all. Thank you so much for listening.